In 1966, a U.S. strategic bomber broke apart in midair over Spain. 4 hydrogen bombs fell toward the ground. The aircraft responsible was the B-52 Stratofortress, a bomber so massive that many engineers once believed it would simply tear itself apart under its own aerodynamic stress. Yet somehow, this aircraft is still flying today. Not just flying, dominating modern battlefields, including operations over the Middle East. And increasingly, the cockpit of this Cold War giant is being commanded by a new generation of pilots, including highly trained female aviators in the United States Air Force. But here's the real engineering question. How can a bomber designed in the 1950s still remain one of the most effective long-range strike platforms on Earth? Because on paper, it shouldn't. Visual, archival footage of B-52 bombers during the Cold War. To understand why, we need to examine the brutal physics of flying something this big, this far, and this deadly. The B-52 Stratofortress was originally designed during the early Cold War. Its mission was simple. Fly from the United States, across the planet, and deliver nuclear weapons. Visual, map showing intercontinental strike route. This meant solving 3 extreme engineering problems. Range. Payload. Reliability. A modern fighter jet might carry 8 tons of weapons. A B-52 can carry nearly 32 tons. To put that into perspective, that's roughly the weight of 5 fully loaded school buses hanging from the wings of an aircraft. And unlike fighters, the B-52 can stay airborne for more than 15 hours. But this raises a fundamental aerodynamic problem. The bigger the aircraft, the more drag it produces. Drag is the enemy of long-range flight. And drag increases with both speed and surface area. The equation is simple. Drag is almost equal to 1/2 times air density times velocity superscript 2 times drag coefficient times area. Visual, simplified drag equation animation. This creates a brutal design trade-off. To carry more bombs, you need larger wings. But larger wings increase drag. And more drag means more fuel. Which means more weight. Which means even more drag. This vicious cycle is one of the hardest engineering challenges in aviation. Many early bombers failed because they simply became too heavy to fly efficiently. So how did the B-52 solve this? With a design that looks strange, but is incredibly clever. The B-52 uses very long, very thin wings. Visual, side profile of B-52 highlighting wingspan. Its wingspan is about 56 meters, larger than many commercial airliners. But the key feature isn't just size. It's aspect ratio. Aspect ratio describes how long and narrow a wing is. High aspect ratio wings produce less induced drag, the swirling vortices that form at the wing tips. This design is similar to gliders, which can stay airborne for hours with almost no engine power. The B-52 essentially uses glider physics, but with 8 jet engines. Which leads to another unusual engineering decision. Most aircraft use 2 or 4 engines. The B-52 uses 8. Why? Because early jet engines in the 1950s were inefficient and unreliable. Instead, and that's the real story behind the B-52 Stratofortress, a machine built in the 1950s that still dominates modern battlefields. If you enjoyed this deep dive into aerospace engineering, make sure to subscribe and join us for more breakdowns of the machines shaping modern warfare and technology. The B-52 Stratofortress proves that great engineering can last generations. The skies may look modern, but sometimes the aircraft dominating them was designed 70 years ago. That's the power of great engineering. If you want more deep dives into the physics behind aviation and military tech, hit subscribe and I'll see you in the next video. If you want to explore more of the engineering marvels shaping our skies and the technology behind the machines that define modern warfare, hit subscribe and join us for the next deep dive. The B-52 proves great engineering lasts generations, and there's more to discover. Subscribe and don't miss the next journey into the machines that define our world. If you want to explore more of the engineering marvels shaping our skies and the technology behind the machines that define modern warfare, hit subscribe and join us for the next deep dive. The B-52 proves great engineering lasts generations, and there's more to discover. Subscribe and don't miss the next journey into the machines that define our world.